Alright, what's up everyone? So today we are going to continue the Form 5 Physics Chapter 3. Alright, so previously you learned about the right hand grip rule in 3.1. Alright, and for today you are going to learn another hand rule, which is what we call the Fleming left hand rule. Okay, so here basically what you're going to study is the effect of the magnetic field produced by two different sources. Okay, one is by the magnet, one is by the conductor. Okay, last week we learned, right, that when you have a conductor and then the wire and then the current is flowing, they are going to produce a magnetic field. Okay, so here you are going to study the effects when you combine the two different magnetic fields right here. Okay, one is from the magnet, one is from the conductor. So when you combine these two magnetic fields, what happens is that the conductor is going to move. So where will the conductor move? This one is what you are going to study today. Alright, so if you look at the first sentence here, okay, if a conductor is placed in a magnetic field, the conductor will experience a force. Alright, the meaning of experience a force is that basically your conductor will move. Okay, so where will it go? Will it go up or will it go down? This one will depend on the Fleming left hand rule that we are going to learn. Alright, so this is particularly, this is actually the experimental setup. Okay, and I apologize for the color, alright, because this one is black in color. Okay, so basically this is a conductor, alright, it's something like this. Okay, so basically what we are saying is that when you have a current carrying conductor and then you put it inside a magnetic field, okay, or you put it inside a magnet, alright, the conductor will move. Basically that is the concept, the idea, okay, because you are combining two different types of magnetic field. But where will it go? Will it go up or will it go down? Alright, okay, so that is what you're going to learn. Alright, so the combination of two different magnetic fields here is what we call the catapult field. Okay, so the meaning of catapult field is actually the combination of two different magnetic fields. Alright, one is from the magnet, another one is the current carrying conductor. So how do we draw the catapult field? Okay, you need to know how to draw the catapult field. So basically, if you look at the diagram, how do we know that here the lines are nearer and then here the lines are further away? Alright, how do we know where does the line curve? Okay, this one is actually very simple. Right, first you look at the direction of the magnet. Okay, magnetic field of a magnet. Remember, it will always travel from north to south, straight lines. Okay, here no problem. But if you put in the circular magnetic field into the straight magnetic field here, they are going to change the shape. So how will the shape change? Okay, I'm going to show you the direction. Alright, so if you see here, okay, because this one is turning anti-clockwise, right? Okay, so rotating anti-clockwise. Now, if you combine the two diagrams, you will notice that the front part, let me cut it into half. Okay, the top part is in the opposite direction, right? Okay, so if it's in opposite direction, okay, meaning they are going to cancel off each other lah, technically. Alright, that is why here the lines will remain straight, meaning the magnetic field here will be weaker. Okay, since you cancel off each other, the magnetic field here will be slightly weaker. Alright, whereas at the bottom, if you see, they are going in the same direction, right? Here, this part, and also this part. Okay, since they are overlapping, meaning here your magnetic field is stronger. That's why here, if you can notice, this part here, okay, your magnetic field lines are actually nearer towards each other. Okay, so basically that is how you draw your catapult field. Alright, overlapping directions, they are going to curve like this, meaning nearer towards each other. So here will be stronger magnetic field, and then the top one will be weaker magnetic field. And then you know, right, since here is strong, here is weak, basically the conductor will move from the strong magnetic field to the weak magnetic field. That's why it's going upwards. Okay, but we have a rule to help us identify the movement of the conductor. Alright, which is using the left hand rule. Okay, remember, since you are watching the video, you are looking at a mirror image. Alright, so you need to make sure that you always remember that. Okay, I'm using my left hand. Alright, left hand rule, okay, or what we call the motor rule. Alright, this one we use to determine the direction of the force. Okay, so three things: thumb, finger, your first finger, and your center finger. Alright, so basically your thumb tells you the direction of the force. Okay, so basically your thumb will tell you where the object will go. Okay, where the conductor will move. Alright, that is the function of the force here. Okay, if my thumb is pointing to the right, meaning the conductor will move to the right. Okay, that is the meaning of this one. Alright, and then your first finger, if you notice here, you have north to south, right? So your first finger, you always point to the direction from north to south, meaning this part is north. Okay, this is north towards south. Okay, you always follow the direction north to south, meaning if my magnet is like this, north to south, my fingers is also pointing north to south. Alright, if it's the other way around, it's like this, right? North to south, so meaning my finger I need to rotate so that it's like this. Okay, that is the meaning. Alright, so basically your finger is the field, or what we call the magnetic field basically. Alright, your center finger will be the current. Okay, they will always follow current. Okay, so these are the three things that you're going to use to identify the movement of the conductor. Okay, so let's say in this case, let's look at this particular example right here. Alright, so try and imagine that you are looking from the front, meaning from here. Okay, if your eyes are here, okay, you are looking from the front. Alright, so basically if I were to draw it, it will be like this, right? Okay, let me just quickly draw this. This is north to south, and then I have magnetic field going like this, right? Okay, and then basically if you were to draw the what they call catapult field. Okay, so you are combining this one with, okay, now if you look here, your current is coming towards you, right? Pointing towards you, so it's a dot. Okay, remember current going towards you is a dot. Alright, so when we draw the magnetic field, we follow the right hand grip rule. Okay, pointing towards you, your thumb points towards you. This is the direction of the magnetic field, anti-clockwise, right? Okay, so anti-clockwise, moving like this. Alright, so when you combine these two, what happens to the catapult field is that you have the conductor in the middle, okay, and then the magnetic field, remember, they are overlapping at the down part, right? So meaning it's going to be like this. Something like that. Okay, you're going to be nearer, and then here it will be further away, something like this. Okay. Alright. Okay, so how do we use the Fleming left hand rule? Okay, now first thing you always do is that you point, alright, your first finger first. Okay, now you set the direction of your first finger first, so from north to south, right? Meaning it's like this. Okay, remember you're watching a mirror image. Alright, so north to south. Now this is what you need to remember. Once you fix the position of your magnetic field, do not change it anymore. So basically it's like this. Once you fix the position of the magnetic field, you are going to lock it. So in other words, it's not going to turn like this anymore. It can only rotate like this. Okay, because a lot of students, they make a mistake is that after they fix the magnetic field, when they search for the current, they are going to change the shape again. So you are going to get the wrong answer. Alright, so always remember, after you fix the first finger, lock it. Okay, make sure that you can only rotate it like this. Okay, do not let it turn around. Alright, fix ready, then it's only like this. Okay, now once you fix the first finger magnetic field, you determine the current. Okay, so current only got two things. One is going towards you, one is away from you. Alright, so in this case, Alright, so if I look from this point, the current is coming towards me, right? Dot. Meaning that the center finger, if you can see right here, your center finger is pointing towards you. So I'm going to show you the whole process again. Fingers, north to south, fix. Don't let it move anymore. Okay, lock it. Alright, and then your current is pointing towards you. Okay, so your thumb will show you the direction of the force. Now in this case, the thumb is pointing upwards, right? So meaning that my force is upwards. Meaning that my conductor will move upwards, hence the diagram here. Okay, so that is how we use the Fleming's left hand rule. Alright, okay, so it's a very important that when you fix your magnetic field, you fix it. Don't let it turn anymore. It can only rotate like this. Alright, so it's just a matter of whether the current is towards you or the current away from you. Okay, so that is how you identify the movement of the conductor. Alright, so that is it. Fleming's left hand rule. Okay, so I'm not going to go into too technical about this part. I'm just going to show you the few important things first. Alright, so effect of two parallel current conductors in a magnetic field. Okay, so to my students, I already apologize for the picture, alright, because it was in black and white. Okay, so the one in the middle here, it wasn't really clear, so I draw a new one so that you can see what is happening. Okay, so basically this one is the magnet lah. Okay, the top and the bottom part is the magnet actually. Alright, okay, so what happens when you have two conductors in parallel? Okay, so you have two conditions here. One is when the conductor is moving at different positions, meaning the current is flowing at different opposite directions. Another one is when the current is flowing at the same direction. So you need to know what is going on here. Alright, so let's look at this diagram. So if I were to look from the top, okay, meaning my eyes now is here. So I'm looking from the top. Okay, top view. Okay, alright, so I'm looking from the top. Okay, so this one is going away from me, right? Remember, if it's away from you, it's always cross. And then if you use the right hand rule, going in, thumb, so it's clockwise. Right, meaning it's rotating like this. Okay, going in clockwise. Okay, right, next one, current flows towards you. Okay, this is away. Alright, so towards you, meaning thumb pointing towards you. Okay, so it's rotating anti-clockwise. Okay, so here if it's towards you, we always put dot and then anti-clockwise. Okay, so what is happening right here is that since they are parallel towards each other, right, meaning this magnetic field, they are going to become like this. Okay, so if you notice, this one is this part here, away, rotating clockwise. This one is rotating anti-clockwise. So basically, if you notice the middle part here, here and here, they are showing that the current is moving in the same direction. If you see here, all these are in same direction. Alright, so basically what will happen here is that you are going to create a force of repulsion. Okay, so basically what happens is that you are creating a repulsive force. Alright, if you flow in the same direction, you are going to repel. Okay, you can just think of it like a magnet. Okay, same pole meaning north and north, they will repel. Okay, something like that. Alright, so the two conductor will repel. No two here. They will repel each other. Okay, this is when the conductor or the current is flowing at different directions, opposite directions. Now what happens when they flow in the same direction? Okay, so when it's flowing in the same direction, meaning both, if I look on the top now, it's flowing towards you, right? They are going to rotate. Both are rotating clockwise. Okay, so we are going to draw it like this. Okay, now if you look in the middle, you will notice that these two are in opposite directions, right? So, same concept like your magnet. Opposite poles will attract. So this neutral point here, okay, what happens is that you are going to create a force of attraction, alright? So basically you are going to create force of attraction. Okay, because it's different poles or different direction, right? So this one will attract. Okay, so remember, if the current is flowing in same direction, parallel, same direction, all right, you are going to create an attractive force in the middle. Okay, not in the middle, meaning you are going to create an attractive force. They will attract towards each other. If different directions, they are going to repel. All right, so that is why the summary here, if you see here, two current carrying conductors flowing in the same direction attract. Okay, if opposite direction, okay, they are going to repel. All right, so your current or your conductor will always move from a higher magnetic field to weak magnetic field. Okay, but basically if you use your Fleming left hand rule correctly, then you will know where will it go. All right. Okay, so that is the first part about Fleming's left hand rule. All right, so the next one you're going to learn is about the factors. Okay, what will affect the force on the conductor? All right, so you have three factors here. Okay, you have number one is magnetic field strength. Second is the current. Okay, the value or the magnitude of the current. Third is the length of the conductor. All right, so if you see here, they have already summarized it for you. Okay, so logically, if you think logically, right, if your magnetic field is stronger, of course the force that you're going to produce will be stronger as well. Same goes to your current. Okay, if you have higher current, meaning you're going to produce higher force. All right, whereas for the length, okay, the longer the length of the conductor, the greater the force. Okay, so basically that is the three factors here. In other words, is all three factors increase, your force will also increase. Okay, so you need to remember this one, especially in your paper 3. Okay, they will ask you to write the hypothesis, right? Okay, learn the proper way of writing a hypothesis. Okay, so if you see here, the greater the strength of the magnetic field, the greater the force. The greater the current, the greater the force. The longer the conductor, okay, the greater the force. All right, so this is the experimental setup. Okay, now when they give you a diagram like this, okay, basically what will happen is that you need to identify the direction of the current. So you need to find out where is positive, where is negative. Okay, if it's not given here, look at the battery. So this is positive, right? Meaning that this one is positive. Okay, so this one is negative. So meaning your current is going to flow this way. Okay, your current is going to flow like this. Okay, this is a brighter color, sharper color. Okay, like this. And then they are going to go through the conductor here. Okay, like crossing a bridge and then to the other side. Okay, so this is the movement of the current. Okay, so if you want to identify the where will the conductor go, will it go left or right? Okay, Fleming's left hand rule. So now if you see your first, we determine is the fingers here, the first finger first. This is north to south, right? So I use green color. Okay, north to south, meaning it's like this. So fix it so that you can only rotate. Okay, next, current. Okay, current is now going away from you, right? If you look at the front part here, it's going inside. So meaning your current is like this. And then if you see that my thumb is pointing to my right. Okay, thumb pointing to the right, meaning that this conductor will move to the right. Okay, so if I were to draw it like this, maybe it will be easier for you to see. Oh, okay, something like this, maybe. Okay, let me just remove this first. Alright. Okay, this is your magnetic field. Okay, your first finger lah, basically. Alright, this one you remember, this is your first finger, center finger, this one is thumb. Okay, I'll write this one thumb first. Alright, so first finger pointing upwards. Okay, and then the current is going in, right? So here, this one is current. Magnetic field, normally the symbol we write is B lah. Okay, and then this one, your thumb will be your force. So meaning that your force will go to the right? So the conductor will shift to the right. Okay, if using your hands, it's like this. Okay, if I lose it in a 2D diagram, then it will be something like this. Okay, first finger, center finger, thumb. Okay, so this one is just telling you when, this is the observation. If you look at observation, when you increase the magnet, okay, the conductor will move faster. Alright, if the wire, okay, or basically if the current is moving, you have more current moving, alright. Okay, this is not the wire lah, basically the conductor. Okay, the conductor. Okay, the mistake here, sorry. Right, the conductor is thrown out at a faster speed and greater displacement if you increase the current. Alright, if the conductor is longer, meaning this one is short, if I increase it even longer, okay, the wire moves at a slower speed and a smaller displacement. Okay, okay, if you look at the observation here, it says the wire moves at a slower speed and smaller displacement, right? This one is because we change the length of the conductor from a longer one to a shorter one. That's why the observation is like this. Okay, so basically if you assume that initially the length is 5 meter and then I change to not 5 meter, 5 centimeters, and then I change to 2 centimeters, what happens is that the wire will move at a slower speed. Okay, that is why the observation here is like this. Okay, it's because we change the length from short to long to short. Okay, so it moves at a slower speed. So basically your conclusion is the hypothesis here. Alright, basically if all three factors increases, your force will also increase. Okay, that is the factors that will affect the motion of the conductor. Alright, strength of magnetic field, current, and length of conductor. Okay, so remember these three factors. Alright, so finally we are going to go into a very important part. Okay, the reason why you learn your Fleming left hand rule where it will rotate and everything is because of this particular section right here. Okay, basically you need to know how what they call a DC motor functions. How does a DC motor work? Okay, now but before that, let's look at this one. Right, this is what we call a current carrying coil. Okay, basically this coil is an example of your DC motor, the one that rotates. Don't worry, later I'll show you an example. Alright, so basically how do we identify the turning of the coil? How will the coil turn? Is it going to turn in clockwise motion or anti-clockwise motion? Alright, so this one we are going to use the Fleming left hand rule to identify. Now first, okay, identify the movement of the current first. As you can see here, now your current is moving like this, right? Okay, so if you look from this part, the front part, you will see that this one is going in, right? So if you are going in, it is cross. So cross meaning that you are going to rotate clockwise. Okay, so I'm going to use my Fleming left hand rule to identify the force for each. Okay, the cross and the dot here. So current going in and current flowing out. So that's why here is dot. Okay, so basically this one is this part. This one, the D to C is this one. And then A to B is this one. Okay, so once you have already identified which one is in, which one is out, you are going to use your Fleming left hand rule to identify the movement or the force, direction of the force. Okay, let's look at the first one. Okay, this one is going in, right? Okay, so maybe if I use this, you can see more clearer. Easy to identify. Okay, draw bigger a bit. Okay, alright, so let's look at this one first. Current going in. Okay, remember, first you fix your center fingers. Okay, so now my fingers is north to south. Okay, meaning I fix it like this. So here is my finger, north to south. Alright, okay, next, I'm going to determine the current. So here my current is going away from me, right? Meaning it's going, so you look at how I rotate my fingers, fix already north to south, and then my current is going away from me. So it's going inside here, right? So this one is my current. So this one is my current. Right. Okay, this one is my magnetic field. So my thumb was pointing downwards. So this one is my force. That's why you see the force is going downwards. Okay, so that is for this one from D to C. Okay, now from A to B, okay, your magnetic field is still the same. There's no changes in your magnetic field. Alright, it's still going from north to south here, right? Okay, the only difference is your current. So now your current is going towards you, pointing towards you, right? So look at how I change. Going towards you, I'm going to rotate it like this, so that my center finger here is pointing towards me. Meaning now your current is moving this way. Okay, so fingers, current, and then my thumb is pointing upwards. Alright, so meaning my force is upwards, meaning that this one will go up, this one will go down. Therefore, if you look at here, since we know that this one is going up, this one is going down, meaning that it's rotating this way. And then later they will rotate back like this lah. It's rotating in a clockwise motion. Okay, so that is how we identify the turning of a coil. Okay, or basically in your DC motor. Alright, okay, so the what they call the parts. Oh my god, I'm getting old. The parts of a DC motor. Okay, first thing that you need to know is this one, commutator. Okay, commutator is the one in the middle here, the two rings here, the two semicircles here. Alright, so that is what we call a commutator. So this one is called a carbon brush. Okay, so basically what will happen is like this. When the commutator, if you see here, touches the carbon brush, then current will flow. Alright, now if you notice, right, okay, the commutator in the middle here, there's an empty gap, there's a space here. So you can imagine when the commutator rotates, right, there will be a certain point where the commutator will not touch the carbon brush because of the middle part here, the empty space here. So when it's not touching, current will not flow. Okay, later I will show you a simulation on what is going on. Okay, so you need to remember the part of a DC motor, or what we call a direct current motor. Okay, alright, basically we are using this to convert electrical energy to kinetic energy. It's basically your toy car. If you have played with your toy car before, you will see this. This one is the so-called the engine of the toy car. Alright, so the one that is rotating is the one in the middle here. Okay, if you open up the thing, this is what you will see. Alright, inside you will see a lot of wires and then coil around the magnet. Okay, and then this one is going to rotate. Alright, so basically that is the DC motor. This one is the DC motor. Okay, so remember when the commutator touches the carbon brush, current flows and then the thing will rotate. Okay, it's just a matter of where it will rotate. Alright, so your job is to identify the rotation of the coil. Okay, alright, so basically just now I already show you how to identify. Okay, so first you always identify where is your current moving. This one is positive, this one is negative. So if you see here, your current is moving in this way, right? Okay, so this one is going in, this one is coming out. Okay, so if it's going in, so remember this is north south, right? Okay, so you fix your fingers. Alright, you fix your fingers. Oops, okay, fix your fingers. Hold it. Okay, meaning you stationarize it. Don't let it move anymore. You can only rotate like this. So now let's look at AB. Okay, AB, my current is going in, right? Meaning it's like this. Okay, so if you were to draw this one just now, so now it's going in. Current here, north, south. This one is my magnetic field. So meaning now my thumb is pointing downwards. Okay, that's why the force is going downwards. Alright, this one you need to try out on your own, then only you can see. Okay, so if I reverse direction of current, okay, so see if I reverse direction of current, meaning my direction of my force also is reversed. Okay, it's exactly the same as like what you learned in your 3.1. you reverse direction of current, your direction of force will also be reversed. Okay, so meaning that this one will go down, this one will go up, right? So it's going to rotate, go up, and then becomes like this, rotating clockwise. DC. Now look at this position right here. This one they are large for you. Okay, so during at this point, it is not touching. Okay, the commutator is not touching the carbon brush because of the gap in the middle here. When it's not touching, current is not flowing, but your coil will continue to rotate because of inertia. You know, once you start moving, you continue to move, right? And since you're already moving in the clockwise direction, and although here there is no current flowing, it will continue to rotate as well because of inertia. Okay, and then it reaches this point. Okay, so now it's already at different side. Initially here is AB, right? So now after you rotate, the AB goes to the left side. So you need to look at your current again. So your current is still in the same direction. Okay, in and out. Alright, so basically it's going to go down, here it's going to go up. It's actually the same thing. Basically it's going to rotate, continuously rotating in the what they call clockwise direction. Okay, and then it's going to repeat the same thing over and over again. So I'm just going to show you a simulation here. Alright, this is a very good simulation because they show you how to use your Fleming left hand rule. Okay, so this one is your magnetic field, north to south. Alright, so you have current flowing. Okay, this one is when it is in straight. Just now you see it's arranged in a flat. Now they're putting in vertical position. Alright, so I don't want to show you this part. Let me show you the back part here where they determine the position of the this one. Okay, so let's look at this part. Alright, so AB, so you see, fix your position and then your current is moving downwards, right? So meaning your force is this way. Okay, if you look at CD, fingers, okay, current upwards. So your force is going to the back, right? Okay, so force front and back, meaning it's going to rotate like this. So you're going to see how it's going to rotate. Okay, so see, that is how they are going to rotate. Alright, so right now if they were to change the direction of the current flow, alright, see how they use the Fleming left hand rule to determine the rotation. Okay, so for BA, fingers first, center finger, and then thumb tells you the direction of the force. Okay, meaning it's going backwards. Alright, fingers, now my current is going down. Okay, this part CD, and then my thumb is pointing forward. Okay, so that you know, the AB is going to turn, meaning it's going to turn in a clockwise direction. So that is how it's going to turn. Alright, so that is the simulation of your DC motor. Okay, right. So hopefully after you've watched the simulation, now you understand how we determine the rotation of the DC motor. Alright, it's basically based on your left hand rule. Okay, look at carefully where is the direction of the current and also the direction of the magnetic field, then you will be able to identify the direction of the force. Okay, so done. Alright, so these are the factors, okay, that affects the rotation of your motor. Alright, basically if you increase the size of the current, meaning that a higher current okay, magnetic strength, and then number of turns. Remember in 3.1 we learned that if you have more coils, you produce more magnetic field, right? So basically the force will also be stronger. Okay, and also increasing the area of the coil will also increase the speed of the rotation. Okay, so these are the 4 factors that affects the rotation of the motor. Basically everything increase if you want to produce a higher speed or basically a larger force. Alright, so that is it for your 3.2. Okay, so normally I don't explain much on the application. Alright, I will only do this online session with my students. Okay, so that is it for the what they call 3.2. Okay, basically the idea is for you to understand how to use your left hand rule to determine the direction of the rotation. for a DC motor. Alright, so I believe that is it for today. Okay, so I will see you again next time. Bye.